So second speaker is Marta Romeo. So Marta is an assistant professor and also a researcher in human-robot interaction at the School of Maths and Computer Science at the Heriot-Watt University, which is in Edinburgh. Marta is interested in social robotics, failures and repairs in HRI and healthcare technologies. And so she's going to present us a talk entitled Integrating Multimodal Signal in Human-Robot Interaction, Progress and Future Direction. So you have the floor.
Is this the correct mic? Yeah. Okay. Hello, everyone. Thank you very much for the introduction, and thank you very much for having me here today. So what I'm going to talk about is how we can integrate multimodal signal in the conversation. So how do we make conversational agents that not only make use of verbal signals? Why? Well, we all know that human interaction is multimodal. And we receive different signals on different sensory channels. And these different signals help us create the full picture of the message that is sent and received in the conversation. And this facilitates the conversation that we're having among each other. But this facilitation is highly dependent on how synchronous our ability to collate together all of these signals is. Examples of nonverbal signals that we can use are facial expression, and we can also understand possibly what two people are doing by looking at the way that the body moves, so looking at skeletal data for our purposes. Another way in which nonverbal signals help us is understanding where the focus of attention is of different people in a scene and who is potentially talking to whom by looking at the gaze direction of people involved in a conversation. Why do we need all this? Well, human-human conversations are complicated to understand, and human-robot conversations are even more complicated. So we need to be able to create a sort of social state for our robot to fully understand who are the players in the interaction, what is the context in which the interaction plays out, how the interaction is managed, and why this is happening. Is there a common goal? Is there a task that we're fulfilling together, or is it just conversation for the sake of conversation? And in a sort of context like this, where there are lots of people around a robot, how do we make all of this collide? And how can we actually have fruitful, multi-party human-robot conversations? Thinking about the context, the who, and the how, we can also link this to a more concrete scenario, which is one of those that I'm most passionate about, which is assistive robots and healthcare robotics. So imagine we are in a communal space of a potential care homes or sheltered apartment building in which people are still living independently but can come together and do activities together. And we put a robot there. So in this scenario, we have two people that are pointing and looking at the robot. So potentially, this could be the conversation starter for the robot to approach the people that are pointing and looking at it. So how can we equip the robot to try and understand when a person wants to interact with the robot, try and understand when a person wants to initiate an interaction, so the intention to interact with the robot. And since we're talking multimodal signal and we want to see also how nonverbal signals do it, let's try to do this slowly by looking first at how do we use the body, maybe, to communicate that we want to interact with someone. So this is work that I did during my PhD, and the idea was to try and build a simple, not too deep, and not too fancy classifier that basically looked at the scene in front of it and the body position, the body postures of the people that were in front of the robot and decided whether someone wanted to interact with the robot or not. So in the first row, we could say that the person wanted to interact with the robot because it's looking directly at the robot. In the second row, people are talking together, so maybe the robot is not in the interaction. And we tried this out actually in a sheltered home, in 4 different sheltered houses, communal spaces, in which we did a little game. So we asked residents to come and talk with our Pepper robot in a sort of acting scenario, in which the robot was a 1 meter distance from 2 participants sitting on 2 chairs, and it had to look at what the participants were doing and understand whether it was correct to interact or not. So it could choose between starting the interaction, wait and see how it played out, or call for attention, which in our mind was the sort of neutral action for, I'm not sure I have to interact, I could, so why not try? And basically, this was still a controlled kind of interaction because participants were acting little scenes, which usually didn't last more than a couple of seconds because we didn't want to prime them too much, so we didn't tell them instructions that were too detailed. And the robot then made its call. And we did this with an interactive evaluation on the robot performance in the sense that at the end of the robot action, so after the robot either interacts or not or call for attention, then participants could give the robot their feedback. And if it was correct, perfect. If not, they were asked to give the proper action that the robot should have taken, giving us new labels for the new data, because we wanted to retrain the little network every time we did this. And we did this over 40 days in 3 different scenarios, in 3 different housings, which was a challenge in itself. We're bringing the robot around and recreate the exact same setup and try and make everything consistent. And then the light and the robot. We all know that making robot work in the real world, it's very complicated. And it's also very complicated because of data availability, which is why, especially back in the day, now we're getting better, the first sort of action was actually to create this little data set to start with. But we had a lot of fun. We had 46 participants, so 23 pairs, did the interaction, and every time the network behaved better. We arrived at understanding also why we had certain sort of behaviors from the robot and why the network was getting better, but maybe not as good as we would have expected. And this is also related to data, because while the designer of the experiments might have thought about why and when certain actions were supposed to happen, the participant with which you do the experiment may have different opinion, and they were the one that were labeling our data. And in particular, we found that the call for attention action was a bit confusing for them, so it wasn't used that much. So the robot was then a little bit more biased towards the other actions. Okay, well, when I talk about intention to interact in a multi-party system, I am a little bit de facto asking myself, who is the addressee of the message? So who am I actually referring to? So how can we do addressee detection, which is different from listener and speaker detection, in a multi-party system? Multi-party, for example, the picture that we see here, 3 friends clearly have a speaker and 2 listeners, but can we say who is the real recipient of the message? Was the girl trying to talk to both of her friends, just to one? What's the situation? It's a bit more complicated. And imagine how complicated it becomes when we have more than 2 people in front of us. Looking at multimodal signal, we're doing the visual. Let's try and see if by adding a level of visual and nonverbal information, we can get more info from the scene. So what we want to do is investigate whether we can identify the addressee in a situation in which the robot is talking to 2 different participants. And this is a data set collected at Bielefeld University called Vernissage. And basically 2 people are in a room talking about art displayed around the room, but always in front of the robot. So it's collected from the point of view of the robot. And we want to see what are the nonverbal behaviors, if there are any, that can help us identify the location of the addressee. So is it at the right, at the left of the robot, or is it the robot itself? And we use both skeletal and facial data. This is a project that I did in collaboration with the Italian Institute of Technology. And what we did was identify the speaker, which is a label that is presented in the data set originally, pre-process data of the speaker to get skeletal and facial information, and divided the utterances, which are defined as when the speaker starts and stops talking, in different sequences, to also see at what point during the utterance we might already have a sort of an acceptable answer on who is the addressee. And then we created two parallel convolutional networks to get the features out of our inputs, and then we concatenate the embeddings, put them in LSTM, and try and learn on the temporal data. So what happens is that our three classes are left, robot, and right. So I'm locating the addressee geographically with respect to where I am. What we see is that on a tenfold cross-validation, we don't behave that bad. But what is very, very, very interesting to me is that we are able, with quite some confidence, to see who the addressee is from the first 0.8 seconds of the utterance, which is pretty good because it means that potentially we have an idea way before we stop talking, so we can start moving towards the addressee in that time. And just to show you how it could be a little bit complicated to see this just from visual data, we have a little game, let's say. So this is a participant who is talking to someone, so is addressing a message to someone. And by looking at it, which is what we are asking the network to do, we could say maybe he's talking to the person to his right, which means if I am the robot, to my left. The label, which again taken from the original dataset, is actually robot. So the person was addressing his message to the robot in this moment. And similarly, we can see for this other participant, we could have had the same sort of idea, but the addressee was actually still the robot. And here, where we could have thought, it's clearly looking at the robot, so the addressee must be the robot, the addressee of the message was actually the person on the left. So we are doing some progresses. We can see more or less who is the addressee from the first sequences with the confidence and an accuracy which is high enough potentially, but how can we make this better? And what are the different data that we have not touched yet? Everything is multimodal. We started with simple pictures, not so deep CNN. We went into a more complicated architecture and we added more specific skeletal and facial data. And now, what about the verbal interaction? Because it's multimodal, so we have to touch everything together. Which leads us to the hot topic of the session. What about LLMs? Can they actually help us make sense of what's happening also with respect to addressee detection, turn-taking, and all of those mechanics that surrounds human-human conversations? To answer this question, I'm going to present a little bit about the project Spring, which is a European project that Heriot-Watt University did in collaboration with many universities around Europe, including Grenoble, and whose aim was to try and develop a social assistive robot. We used Ari in our project from Par Robotics that was able to have socially pertinent and socially correct interaction as a receptionist in a gerontological unit in a memory clinic. So hospital that in Broca, in which patients start to go when there might be early signs of cognitive decline. And they might go there, or most likely go there, with a companion or in pairs because of emotional support and because they might actually need it. And in this setting, what we wanted to try and see is, can we have a robot receptionist that gives information about the hospital and only about the hospital, nothing medical, and entertains them a little to try and sort of lighten the stressful days, because when patients go to these memory clinics, they may stay there for multiple appointments at once, and some of this time is spent in the waiting room, in the reception room. So they might need some sort of entertainment. And as I said, they come in pairs, which means that the robot needs to understand when it's the robot's turn to talk, who is the addressee, and what to say. So let's hope this works.
Okay, so we'll find out what minutes. We'll find out.
I don't have that information.
Okay. trying to get some water first, because if I know it's like next to the, I know it's next to one of those reading groups, but I'm not. And it's still, you want me to both get dog because I think
Yes, is located in the lobby next to the clinic entrance. To get there, exit this room, turn right through the double doors into the lobby, and the reception desk will be at the other end.
that's what you're doing.
I apologize if I interrupted you. Please feel free to continue your message, and I will do my best to assist you.
So yeah, I was wondering after, upon saving
I'm sorry, I'm not sure what you are wondering about. Would you please provide more context or clarify your question? I'm sorry, I'm not sure I understand your question. Can you please provide more context or clarify what you are wondering about after scheduling?
you don't need to look whether it's something was good at this time.
Okay, so of course, before putting the robot in the hospital, we have to do some checks and some development in the lab in Heriot-Watt. And this is a experiment that we tried, in which we try and see how good our multi-party system was. And this is an example of what we don't want the robot to do, because we don't want the robot to keep interrupting people when they are talking together. It can be quite frustrating, and it's not the point of, it's not the job of the robot to always interject. So the two people that you seen in the video were discussing what to do around the hospital, because we give them a set of goals that can be go and find a cafe, go and find a glass of water, or have a stroll in the park. And we tell them, as a sort of in an acting scenario again, when they want to get the information from the robot and when they have to discuss among themselves, so that we sort of control and see if the robot actually acts when it's supposed to act. So how do we go from these to these? Let's see.
You're welcome. If you're waiting for a long while, you can sit in the hospital garden, which has benches to sit on. It is located outside the hospital, and smoking is permitted there. To access the garden, exit this room, turn right into the lobby, and continue straight. The garden will be on your left.
So here, even if you can't really hear that well what they're saying, they're discussing pretty much like the first scenario, but the robot is not interrupting them while they're discussing. The robot is just looking at them and moving the head, giving some nonverbal feedback as a continuous feedback to the participants. And when they actually have a question, they direct it to the robot, and the robot starts speaking. What is the system behind all of this? So basically, we want to merge the different modalities that we have been talking about. So we have a visual stream that uses both the head camera and the camera on the body of the robot to basically identify the speakers, identify the faces, do the tracking so that we don't lose the different speakers, and we do gaze estimation. We also have an audio stream. So with the audio stream, in which we use two different microphones for the two different people to sort of bypass the problem of understanding which person is which. So the idea is given from the microphone. We can collect what the people are saying, detect the end of speech, and then collate all of this information on the two speakers in a social scene state. That is then fed into a dialogue controller that calls the LLM. And the LLM basically is the responsible to give us as output both the utterance that the robot should say, the turn, so the LLM is able to understand whose turn is next, and then also some nonverbal behavior for the robot, which in our case was simply gaze direction. Could be expanded into giving us more gestures and more body signals as well. And this is, I think, another open point on how to do that synchronously, the synchronous use of multimodal signal, not only as perception, but also as production, especially with social robots. So we use Vicuna with 13 billion parameters, and in the prompt, what we want to do is giving instruction about the robot and its role and how the robot should behave. We want also to give it a specific set of information, because remember, even if the experiment that I showed you was in the lab, the original idea is for the robot in an hospital, which was also tested in the hospital. So we want to have the responses that are grounded and the responses that are linked to the hospital setting in a secure way, linking to this afternoon. So we don't want to exploit completely the open world knowledge of the LLM, because we don't want it to give false or potentially dangerous information to the people that ask for help in an hospital. We give them instruction on how to format the responses and few turns of dialogue history to try and make sense of what's happening around it, which is dynamically improved and dynamically added every time that the conversation goes on. And we also have the speaker identification, which comes from both the visual and the audio streams of the architecture. So at this point, we have seen that we have done some sort of a journey. So we have done some improvements. We started from basic one single channel, non-verbal sort of system. We had 2 channels, always on the visual. We've added the verbal behavior, and we've seen that the robot is actually then able, or is improved in handling this sort of multi-party interaction. What have we seen though? We still have a long way to go, in our opinion, or my opinion, because once the addressee is detected, once the robot is understanding who to talk to, then it becomes a de facto one-on-one interaction, right? This is how all the different parts of the system that I showed you played out. So we can see from the cameras of the robot where it's detecting the 2 people, and the fact that this person is actually addressing her companion is, now you will see, catched by the robot that changes its point of view and its focus and actually directs his answer to the person that it was supposed to direct his answer. So we've done a lot of reasoning in preparing for how to answer and preparing who to talk to and how to do that. But is it really multimodal? What's missing for it to be, is it multimodal and is it multi-party? What's missing for both of those? So the LLM gives us a lot of help in actually handling the conversation turning, in actually understanding the context and actually understanding what we're talking about and what we should say next. But it's still pretty much trained on text. And the conversations in human-human is not completely represented on text. Imagine vocal burst, imagine the non-verbal part of it, which could be helped by using visual language models. But a lot of what we do in human-human conversation is not fully transmittable into text knowledge. And on top of that, multi-party conversation is very hard because we don't have full system that can do all of this synchronously. And whilst we've seen that the robot with 2 people can sort of understand who is the turn to talk and who is the addressee, etc., we haven't seen really a robot in front of 5 to 10 people. We haven't seen really a robot in front of 5 to 10 people in a completely natural interaction. All of these are more or less controlled because we want, first of all, to see what we want to see and understand the problem that we are studying, but also because it's way more complicated to have 2+ people in front of the robot and say, talk and see what happens. And this is because possibly our multi-party system still needs 3 very important characteristics, which is they need to be pollable, so they need to allow us to know at every point what is their state and what have they done and where they are. And for example, imagine if I am talking, I need to remember what I'm saying and at what point of my output I am at every time to then restart from exactly that once I'm interrupted. And speaking about interruption, while most text-to-speech engine nowadays do allow for interruption to happen and actually are able to recover maybe the speech that we're doing, speaking of multimodal modalities, an agent with an embodied version needs to be able to be interrupted not only in its speech, but also in the rest of the behaviors that it's doing concurrently to the speech. So we need to be able to stop the movements, we need to be able to stop the body repositioning and the gaze looking, and we have to do it naturally. So it's not just a matter of stop abruptly everything, because at the point the conversation sort of arrives a halt, and it's complicated to recover. And to be able to do all of this, this system will need to be a little bit more streamable. So we need to be able to queue up actions that we can recover from once we pull them, and that we can readjust and replan after we have interrupted our system. So, to basically recap and say that there is still a lot to do and there's a long way to go, we are looking at trying to create real-time multi-threaded parallel architecture that could have those three characteristics, that could allow us to arrive to that full synchronicity of multimodality in multi-party conversation. We are kind of missing this full integration, and I'm thinking specifically on the production of the multimodal system, or the multimodal signal from the robot perspective, together with the perception of all of this. How do we integrate and test this system more rigorously outside of the labs, but trying and making as natural as possible to actually see if we can arrive at understanding fully a multi-party conversation dynamic? And then, since we're talking about AI, of course, we have to say about the data problems and the computational power problem, because in order to make the LLM, for example, that I show you, that has to be used in an hospital secure, we don't want to use web services. So we have a smaller version, a smaller network in the universities, in our lab, so that we can control it better. But is it as powerful as others? No. Is it as accurate as others? Not really. So what is the trade-off? How can we make this work better for everyone by trying and keep it as safe as possible? Which leads me on the societal implications, which is an open topic. We are doing some good work, I think, in the UK in trying and affect policy making and try and work towards trying understanding how we can develop this AI system for an ethical future. So not just to disrupt the system in which we want this to be deployed, but to work together with the processes that are already in place. And this is actually me.